Hello, you're listening to Inside iOS Dev, a show about real-world iOS development, here with your host, Andrew Rohn.
And Alex Bush.
Today, we have a special guest, David Kopec. He's here to talk about his book, Classic Computer Science Problems in Swift. He's also an assistant professor. He's written an introductory book on Dart in the past. He's also done consulting, so he has quite an interesting resume. I guess, Dave, if you can go ahead and introduce yourself and tell us a little bit more about yourself.
Sure, absolutely. Yeah, it's an honor to be on the show, by the way. I'm a fan of the show. You covered most of the bases. I'm an assistant professor of computer science at Champlain College in Burlington, Vermont. I used to work as an iOS developer, mainly as a consultant, helping early-stage startups build their first iOS apps. And I'm also the author of Dart for Absolute Beginners, about the Dart programming language, in addition to Classic Computer Science Problems in Swift, which we're here to talk about.
Great. Thanks for joining us. So I guess to start off, can you just kind of give us an overview of this book and just give us the gist of it?
We call the book a great second book on Swift. So it assumes Swift knowledge. It's not a book that's going to teach you Swift from first principles. It assumes you already have a basic knowledge of the syntax and semantics. But then it's a broad book. It's not a deep book. It's a broad book. It goes into a lot of little computer science topics, some big computer science topics, without getting really deep into any of them. It's more of a survey book. Perfect for people who want to refresh on their computer science education. Maybe it's been a few years since they were in school. Maybe you're doing some interview prep, or maybe you're a student in college right now doing computer science and you want to do computer science in the language of your choice, Swift.
Great. So can you go ahead and kind of what are the specific problems that you go over in the book?
Yeah, it's quite a range. So it's everything from search algorithms to genetic algorithms, graph algorithms. We even go as far as doing a little machine learning towards the end of the book, k-means clustering and neural networks. So it's quite a range. And I hope there's a little bit of something for everybody. Without getting into each of the individual topics right now, I think if any of your listeners looked in the table of contents, there'd probably be something they'd say, hey, I'm interested in that, and I'd like to know more about that.
So, David, that is actually kind of one of those things we were interested in and curious about. Who would be in what is the use case, I guess, for this book and kind of learning those topics? Maybe actually going individually through them.
Yeah, absolutely. Sure. So let's go through it chapter by chapter then. So chapter 2 is called Search Problems. And that is so fundamental. I mean, anybody who's working in computer science, doing software development, needs to understand search. Because if you're doing a linear search when you should be doing a binary search, your program's just not going to be very performant. So that's just such a fundamental basic skill set that we expect everybody to have. And at the end of that chapter, we get into A star, which is an algorithm used oftentimes for path planning, making efficient paths in, let's say, something like a game. But it can also be used in most contexts where you need a search and you have a little bit of a heuristic, a little bit of extra knowledge about the kind of search you're trying to do. So that chapter is very widely applicable. The next chapter is called Constraint-Satisfaction Problems. So constraint satisfaction problems are things like a scheduling problem. You have a bunch of people who need to be in a certain place at a certain time. Your constraint maybe is who needs to be there and what times they're all available. How do you efficiently find a time for everybody to meet? That would be a constraint satisfaction problem. Chapter 4 is graph problems, graph algorithms. So if you think about something like a transportation network, something like the subway system, how do we find a route through the subway system that connects every single station on it with the least amount of track? How do we find an efficient way of getting from one subway station to another subway station? Those are the kind of problems that graph algorithms are great for. Chapter 5 is genetic algorithms. So those are great for problems that we don't have a well-known solution for. Because genetic algorithms work a little bit like evolution in biology works, where you try a couple different things. The ones that work better, you keep them. You try modifying them and mutating them a little bit, and you keep going with a little bit of randomness, hopefully getting closer to your ideal by the end of it. So any problem where you don't have a good algorithm for it, you might want to try a genetic algorithm. Chapter 6 is on k-means clustering. That's a type of unsupervised learning. You have a bunch of data. You want to somehow organize it into clusters. K-means clustering is a way of organizing that data into groups without necessarily knowing what those groups should be ahead of time. Chapter 7 is neural networks, which is really buzzworthy right now. Of course, very popular in deep learning. I think that everyone should understand how they work. So in Chapter 7, instead of using a framework like TensorFlow and learning to use a framework, you actually build a neural network from scratch in Swift, using nothing more than really the Swift standard library. So you really get an understanding of how do these very advanced computational techniques work from first principles. And then the last chapter is on miscellaneous problems. It covers things like minimax for chess or checkers or tic-tac-toe. The traveling salesman problem was just a famous computer science problem that most people have probably heard of. And the knapsack problem, which is when you have a certain amount of items that you need to fit in a knapsack, how can you efficiently choose which items to take, which are the best items to take? And you can imagine how that could be applied to other types of problems.
That sounds very interesting. That's a very broad scope of problems and that you're tackling in the book. What I'm wondering, to me, it sounds like, I just kind of guess from my personal experience working as primarily an iOS developer day to day, I would say starting from chapter 3 and actually, the rest of them sound like problems you would solve on the back end, let's say, right? Rather than on the client side when, let's say, you build an iOS app. Would you say that's a fair statement, or there are scenarios where, in cases where you would want to, I think you mentioned a game or something for finding a path.
Yeah, no, it really depends. I think we would have to talk about a specific application. I think you're right for the most part. Anytime you're going to be dealing with big data, you're obviously not going to be doing that on device. So if you're working with a really large data set, you wouldn't use any of these techniques on device. On the other hand, yes, there are specific applications where it would make sense to do it on device. One would be games, of course, just because you need an instantaneous computation. Others would be when you're dealing with smaller sets of data. You can imagine, let's say, a health app that has data about its user and it needs to cluster that data. And for privacy reasons, you don't want to be sending all of that data to a server, right? In that case, you might want to run something like k-means clustering to cluster that health data right on the device so that you avoid any privacy concerns.
I have a follow-up question about that. And I don't want to sound like we're being too pokey, but I think me and Alex are coming from like the practical development world. And like these kind of sound academic. For example, like I agree, it's useful to know the different search algorithms, but for example, you likely, if you're implementing your own search algorithm in your iOS app, you're likely doing it wrong. You likely should be just using what they give you out of the box, or these other things like the k-means clustering. So do you think for regular developers such as ourselves that this knowledge is still useful? Given that?
Absolutely. So that's a great question. And, I agree with you that most developers do not want to be implementing them themselves. And some of the implementations in the book are a little bit naive. I would be horrified to find out that people were taking some of the code from the book and using it in a mission critical production app, because the idea of the book is to introduce you to these techniques so that you know which one to choose when you pick a library. Absolutely. You should be using the standard library as much as possible. You should be using well-supported open source projects as much as possible. But you need to ensure that you're using the right one. So if you're using k-means clustering when you should be using a neural network, you might be making a big mistake from the get-go. So knowing for which tool to reach for, this book can be really helpful with that. The other side of it is I think you should understand what those libraries are doing behind the scenes, even if you're not going to be an expert and ever implement them yourself. I personally just have that curiosity, but also if you're ever going to be somebody who works with really complex problems, not just API mashup, but working on problems in data science or working on problems in, let's say, the healthcare space, as we mentioned earlier, you really need to understand how the data is being manipulated. And so I think it depends on the application you're working on. But in general, I think everyone should have a broad overview of how these algorithms work and then know which one to reach for in a particular situation, which is why at the end of every chapter, we have a little section called real world applications. And it tells you what kind of real world application would you want to use this technique for.
Yeah, actually, I think that's a really good explanation. So with me, I had a computer science education. I had my bachelor's in that, and so we did things like, I took an assembly class, and so like obviously I'm not writing assembly day to day, and I probably shouldn't be. But I still feel like there's this fundamental lower level details that other people who I work with or who I've worked with on a project who don't have that understanding. There's a little bit of a disconnect, and I can tell there's just like not that deeper understanding. And so the way I think of it is just like I have this appendix of at least knowing where to go. For example, like you said, with like between choosing different algorithms, I just have this appendix of like, I don't have them memorized and I don't think I'm going to write them from scratch, but I'll have this appendix of like, okay, there's this problem area. And I remember from my education that these are the options. So I think that was I know I use that kind of heuristic personally.
Yeah, I totally agree with you. And, you bring up another great audience for the book, which is self-taught programmers. We know sometimes there are people who are self-taught who are way better than somebody who has a degree. They might be the 10x engineer, doesn't necessarily have a computer science degree. But maybe they want to brush up on these topics that they missed out on by not having that computer science degree. And so this will give them a broad introduction to a bunch of them.
Well, in my case, I also have a bachelor's in computer science, but somehow with my education, a lot of those were skipped or not covered. So for me, I'm sometimes finding myself where I'm in such a situation where I just need a book, like a reference or something, that goes through all of them, tells me what they're about, and maybe, it gives me an example of like real world application of that algorithm or that solution. So that makes sense.
At the same time, we tried to make the book approachable. We didn't want to make it like a textbook. So you could, of course, pick up Introduction to Algorithms by Corman, or you could pick up Algorithms by Sedgwick, which are the most famous algorithms textbooks. And you'll find a ton of math and a ton of proofs. And there's nothing wrong with that. People need those references and they're great books. But some people want a more approachable introduction that doesn't require as much of a mathematical background. And that's what we were shooting for with this book.
I'm wondering why Swift? Why did you use Swift for this book?
So when the book started, I started working on the book in 2015. There weren't any data structures and algorithms books in Swift. And so I thought there was a niche here. There's people who are self-taught programmers or who are coming into Swift and don't have that CS background or want to brush up on it. And now there are a couple other books in this space, but I think my book is unique in that it approaches it from a problem perspective instead of from a purely data structures and algorithms perspective. So instead of saying, here's the data structure, here's the algorithm, we say, here's the problem, how do you solve the problem? So Swift, also, I just love Swift. I'm very involved in Swift myself through open source projects. And I thought that Swift deserved a good book that introduced these classic computer science problems.
Great. I guess I'm curious to if we can dive kind of into one of these here. I'm actually interested in the genetic algorithm chapter here. If we can go into that a little bit, because actually I've heard of the term, and to be quite honest, I didn't even know what it was until you just explained it. I mean, I had a sense that it was probably something like that. Can you kind of maybe talk about genetic algorithms a little bit? I find that interesting.
Yeah, absolutely. And I should preface this conversation. I'm going to quote one of the authors of one of these data structures and algorithms textbook. His name's Steve Scianna, and he wrote one of the big texts. He said, "I have never encountered any problem where genetic algorithms seem to me the right way to attack it. Further, I have never seen any computational results reported using genetic algorithms that have favorably impressed me." So I'm going to preface it with that by saying that one of the experts in data structures and algorithms says, you know what, genetic algorithms are not necessarily your best choice. You should use genetic algorithms when you really can't find any other solution to the problem. Let me give you an example. The traveling salesman problem is a famous problem where you have a salesman, he has to visit a bunch of different cities. What's the most efficient way for him to visit all the cities, assuming that he can go from any city to any other city and needs to come back to his original destination? That sounds like a pretty simple problem, right? But it turns out and UPS, if you think about UPS or FedEx, they have that problem every day. How do they most efficiently deliver all of their packages, right, to every house or business that they need to deliver them to? There's actually no efficient algorithm to solve that problem for a large number of cities, which you might find surprising. So you could approach that problem using a genetic algorithm, and there have been some results that have been quite impressive using genetic algorithms to solve that problem. So it's not a technique I would reach for as a first choice. It's a technique you reach for when you've kind of exhausted your first choice, or maybe you can't even think of a first choice.
So that makes sense. And you mentioned that the way and the reason why it's called genetic, it's evolving, right? So how does that work?
Yeah, absolutely. So you have some kind of problem you want to solve, and you have something called an objective function or a fitness function, which tells you how close are you to solving that problem. So it just checks, okay, given the current solution I found, how close is it to being the right solution? You measure that fitness function through every generation of the algorithm. And what do we mean by a generation? You have a bunch of individuals who are different potential solutions to the problem. You measure each of them. The ones that are close to maybe solving the problem or closer than you've been before, you take them and you cross them over. You combine them together in some way. Just like in evolution, you have parents create children. And then those children get some of the traits of the good solutions from the last generation. And then you mutate them a little bit. So you might make a really small change somewhere. So that's where the randomness comes in. There's also a bit of randomness in who you've chosen to mate. And then you do it again. Then you have a new generation of individuals who are potential solutions to the problem. You measure how well each of them solves the problem. And the ones that seem to solve it pretty well, again, you cross them over, have some children, mutate the children a little bit, and you keep going until you found something that solves the problem to some threshold that you define as a good solution.
So to me, and I have a very amateur knowledge of machine learning, right? That sounds like a machine learning way of doing it, right? Mm-hmm. Where you kind of have I forgot how they call it, but they split the data in the test set and the other set that you run against, right? And then basically the machine is learning, right? And with every iteration, you check the results it spits out against the set that you verify with.
Yep.
Is that similar to that?
Yeah, there is a relation. In most neural networks, for example, you use something called gradient descent, which you can think about like rolling down a hill towards your solution of the problem. So getting a little closer every time you approach the problem with each iteration. Genetic algorithms are similar. Every generation, as we call it in genetic algorithms, we get a little bit closer, hopefully, to solving the problem. So yes, there's definitely a similarity there.
Can we talk about also the k-means clustering? I think that's a machine learning technique.
Yes, k-means clustering is an unsupervised machine learning technique. And what that basically means when we say unsupervised is that once we start the algorithm, we don't touch it. We let it just run on its own till it gets to some kind of solution. In k-means clustering, you have a bunch of data points, and you want to somehow divide those data points into groups, sometimes called clusters. And what you do is you in the traditional algorithm, you choose some random points to start as the centers of your clusters. Then you measure all of the points. Which of those centers are they closest to? You assign them to the centers that they are closest to. And then you calculate new centers based on all the points that were closest to the last center. So you keep iterating, moving your center as you figure out where they are closest to of the new centers. So again, it's kind of like generations. And through every generation, you get closer to the points not moving, to the centers not moving. And when you no longer are moving, then you're done with the algorithm and you have your clusters. So the concept is you have a bunch of data points. What are the clusters? And if you don't really know ahead of time, k-means clustering might help you find what the groups that are within those data points are.
Great. That was a great explanation. Yeah, I find these very they're somewhat academic, and I don't mean that sort of as taking something away. And to me personally, I like these kind of problems because I think what they do is they stretch your brain, and they make you work basically mentally. And so for me as Alex knows, I'm a constant learner. I love learning literally about any topic, because I think all knowledge you can. There's a lesson that you can tie things together. I mean, literally from history to art, you can tie things together and learn things. And I feel like this is one of those things where you're somewhat straying from the everyday kind of, oh, I'm trying to get this button to like change colors, right, to like, this is like a more academic. But I think what this is useful for is stretching your brain, and also allowing you to know what options are out there, so that when the hard problems come up, people can come to you as kind of an authority or to help solve the problems, or at least know like where to start. So I think for me personally, that's what I find useful about this book.
Great. Yeah, no, I totally agree with you. It is a way to stretch your brain and stretch your thinking a little beyond what sometimes is derided as API mashup, which I think all of us as software developers get into that at some point in our career, where we're kind of just mashing a bunch of libraries together and putting a nice UI on top of it. And we stop doing deep thinking. And I think this book is an opportunity for those of us that have gotten into that rut a little bit to climb out of it.
Yeah, that makes sense. For me personally, I'm actually, like, throughout this whole conversation, I've been thinking, how can I have a project of mine, and I think I actually can use some of these techniques there, because I'm working on a small client-side app, Mac app, and I will have actually a lot of data to process, and in some cases I need a sort of a pattern recognition thing. And I feel like maybe reading this book, I'll pick up some ideas on how to apply, let's say, a neural network for that.
Yeah, absolutely.
Maybe. At least it gives me ideas already.
Yeah, and that's the idea. It's to spur ideas. You're not going to come out of this book being an expert on any of these subjects, but you'll at least know what they're about. And if you're in a conversation about them, you'll be able to talk about them intelligently. And like we said, you'll be able to pick a good library to use that's appropriate for the type of problem that you're trying to solve.
Do you think this is also useful for people who are preparing for interviews as software engineers?
You know, I think it is. I know that Alex, you have a great iOS interview guide, and I think that's a fantastic resource that everyone should use. I think if on top of that, you don't have a background in computer science, like you don't have a bachelor's degree in computer science, I think this book would be a good addition to that, because it'll introduce you to some of these computer science topics that you would have been introduced to in a bachelor's program, or maybe you just want to refresh on them in Swift, because you maybe did them 10 years ago in Java or in Python while you were in school, and you haven't seen them for a while. And unfortunately, I don't know how you guys feel about this, but you know, there are whiteboards in interviews. I'm sure, Alex, you have an opinion on that.
Oh yeah.
And sometimes they'll say to you, hey, can you show me something like a binary search, which is in chapter 2 of the book? Or can you explain to me how to set up a graph data structure for this, which is in chapter 4 of the book? You might want to have refreshed on that before you go into the interview. And I think if you've been doing Swift recently and not Java or Python, this is the perfect book for you to refresh on those topics.
Yeah, David, that was a great segue into that, because I was going to say that I, like, in my book, I intentionally skipped all of those topics. Algorithms specifically, yeah. Because that, first of all, it wasn't my core competency, right? I can't really authoritatively talk about that. But also, it's a different thing, right? Even if I do it in Swift, that's a like we've been talking about it for 20 minutes, right? It's a different set of problems from, let's say, just simply iOS problems.
Yeah, and iOS is so deep. I think it would be impossible for one book to cover iOS interview prep and also data structures and algorithms interview prep. These are huge topics. And I think, unfortunately, today, with how competitive whiteboard interviews are, people really need to be as thoroughly prepared as they can be.
Great. I guess I want to wrap up here soon, David. I just want to let people know we're going to have a promo code for this book for special for our listeners. Can you tell them about that, Dave?
Yeah. If you use promo code PCKOPEC, PCKOPEC, on Manning's website, manning.com, you can get 50% off the book, which is really a pretty nice discount. So I hope your listeners will take advantage of that. Great.
And I also believe we're going to have a book giveaway with Manning. So we'll go ahead and put both of these in the show notes for the listeners, so you guys can check that out. David, was there anything else you wanted to add or close out with?
Well, if readers have feedback for me about the book, I love to hear it always. They can reach me on Twitter at Dave Kopec, DaveKopec. Love to hear from readers always.
Awesome. Thank you, David, for coming. And guys, read the book, Learn Algorithms.
Thanks a lot, Alex and Andrew.
Okay, take care, guys. Thanks for listening.
Bye.